Hello everyone. In this video lecture, I'm going to solve a heat conduction in a finite slab. It is a typical one-dimensional heat conduction problem of unsteady state. This equation is the governing equation for the one-dimensional unsteady state heat conduction problem. In order to simplify the problem, I just used these parameters to convert this equation into dimensionless form, which is given here. Accordingly, initial condition also changed as per the new parameters. Also, the boundary condition also changed as per the new parameter. In this problem, I want to compare our CFD solution, that is COMSOL solution, with the analytical solution, which is given here. The problem statement is a heat rod initially at temperature of T1. When time equal to 0, the step input is, that is step drop in the temperature at the both the boundary is given by this equation. Now let us solve this problem in the console. Open the console, click on model. This is since we're going to solve one-dimensional heat conduction problem, let us select 1D, and the heat transfer, let us select heat transfer in solids. Add, click on study, then choose time dependent since we are solving unsteady state problem. Click on done. After selecting one dimensional heat conduction problem, since we converted our governing equation into dimensionless form, I'm going to select unit as none and the component 1 and the unit system just select none. Then right click on geometry, select interval and replace the 0 with -1. Then build all objects. Now we have created geometry length between -1 to 1. Since we also converted length as well as into the dimensionless form, it become -1 to 1. Now let us define two things. First thing, let us define a step function for the sudden temperature drop from T1 to T0. For that, click on definition. Under that, just click on more function, click on step. Under location, type 1 e power -6. Then it changes from 1 to 0. Since our temperature dropped from 1 to 0, just type 1 to 0. Then click on smoothing function. Here, just give the size transition zone. We can visibly verify that this size transition zone here minus, sorry, 2 e power -6. And click on plot. We can check the transition zone from 0 to 2 power 2 multiplied into -6. After defining the step function, let us define another non-local parameter. Right click on definition, click on non-local coupling, click on integration, and select all the domains. Select all the domains. Yeah. Now our definitions are over. Now let us move to the heat transfer in solids. Before that, let us minimize the definition as well as the geometry. Now click on solid, and the solid just let us give all those parameters. A as 1, density as change into user defined, and CP as 1. Now let us check the initial values. We know that the initial temperature is in dimensionless form, it is 1. And now I want to define the boundary condition temperature. For that, just click on under physics boundary, click on temperature, and since both boundary conditions are exposed to the new condition here, all boundaries, so both the boundaries are selected here. Now we should not write 0. Instead, we have to go for the step function. That is nothing but step 1 of function of time. This step 1 is nothing but only the parameter. The step function we define here. Then our physics over now. Now let us go into the meshing part. Click on mesh. In settings, under sequence type, click on user controlled mesh. Now we have two new options. Under size, click element size. That is under size. Okay, the element size here. Final. Now click on H1 and click on geometry here. Select boundaries. Click on H. Select let it let me check that. Right click on edge and click on size and select boundary and select all boundaries and locate element size and choose custom, then click on maximum element size, that is 1 e power minus 4, then let us click on build all. Now our meshing is generated. Now let us go to the study, click on study and click on time dependent. The time dependent just change the value, that is output times from 0 to the step of not 0 0.1, 0.01 to make sure that the transition of boundary temperature from 1 to 0 is represented correctly by the transition solver. Use an initial time step that is smaller than transition zone of step function. Let us click on under study, click on show default solver. Under model builder, let us click on time dependent. Under time dependent solver, click on time stepping here. Click on initial step and type 1 e power minus 3. Sorry, uh, 2 e power minus 7. Then under maximum, we need to look for maximum shift constraint. Let us click on constant and type 1 e power minus 3 and now compute. Now our solution is converged. Let us now tune them our results. Just drag down and we click on temperature line graph. Here under temperature, let us select only few time list. That is from the list, let us select 0.1, 0.2, then this 0.4, let us go, then 0.1, let's go, that is here. Then let us go to the 0.2, 0.2, then let us go to 0.4. We need to go for long way. Yeah, 0.4, then let us finally select 0.6. Now let us plot. You can check oh, plot. That is the temperature distribution along the length, the x coordinate. Now let us fine tune the graph again. Now click on line graph, click on coloring and stain, and let us go to the line marker here. Let us select cycle. Then let us go to the legends, select manual, then type yeah, select 0.01 second. Let me take that is slash TAU equal to 0.1. Let me copy this value so that let us reduce the time. Then let us plot the graph. Let's go to the temperature again. And in the lines up, kindly select show legends. And our legends are shown here. That is the temperature profile along the x direction. Now let us plot the relative error that is between the CFD solution as well as the analytical solution. For that, again, add plot group. Let us go to the results. Let us go to the 1D plot group and let us give the name to that relative relative L2 error in the label. Then let us click on line graph. In the settings window, let us choose all the domain. All domain. We go to the y-axis data. Yeah. Here, remove temperature. Already I given. I just taken that equation. That is analytical solution. The equation form. Let us put these values here. Under description, let us select here. Let us write L2 error. L2 error from analytical solution. Now X data. Let us select it from expression. This is time. Then under color and style, let us choose from theme and let us flat. Yeah, this is the relative error. We can verify here since we are going to step into the temperature. There is a different relative error is not zero near to the starting condition. In all the condition, both analytical solution and our CFD solution merges. That's what error lies on zero. Let us fine tune this graph so that we can get better visualization. Click on relative L2 error. In that manual x-axis, that is a manual axis limit. Click on minimum value of x minus 1 e minus 3 and y maximum. Let me give 1 because maximum you know that is a 1. Similarly, y minimum let me give the 0 and y maximum let me give because error always lies in 0. So let me give the minimum value 5e power minus 4 and let me plot the graph and we can check the graph very visually only at the step input function that is a physically valid one. Our error is not 0. We can check here only at starting position the error is not 0. In all other cases, error is 0. That means our analytical solution as well as the CFD solution is merges. Therefore, error lies on 0. Thank you for watching the video. Thank you.